All right, this is a very succinct introduction to something known as eigenvalues. If you know German, eigen somehow, I guess it relates to characteristic. Maybe that's what it actually means. That's just how I'm aware of it. An eigenvalue is just known as a characteristic value, and an eigenvalue with respect to matrices is known as, like, if we have a matrix A times a vector x, this is going to be the same as lambda. Lambda is the symbol for eigenvalue times x. And so really here, this lambda again is the eigenvalue. And then this x here, this x vector, is again the eigenvector. And so really this is a characteristic value. So again, depending on how you apply your linear algebra, this can be seen as an important data point. For example, one application I can give you off the bat is if you're dealing with something known as Markov chains, which can help you predict stuff like weather. The eigenvalue here will always be 1 for your characteristic vector, which is again your eigenvector. And so that's an example, at least on the top of my head, but depending on how you apply your linear algebra, the eigenvalue can be a very valuable data point. And so really, if we want to actually find our eigenvalues, so I mean, in order to do that, it's really the determinant of A minus lambda I must be equal to 0. And this is how we solve it. And again, the reason why this should hopefully make sense here is, first of all, if we actually look at this matrix equation here, if we do AX, we move this to the other side, AX minus lambda x equals 0, and then we just factor out an x. Remember, with regards to multiplication and with matrices and vectors, again, this has to always be on the right side, this x vector. So if we rewrite this as A minus lambda, and remember, because A is a matrix and we can't do a matrix minus a number, this will be times the identity matrix in the same dimensionality as A. And remember, A has to be a square matrix because otherwise we can't do the determinant of a matrix that is not square. So A minus lambda I, and then this times our x vector will equal 0. And then here, hopefully, this reminds you of this AX equals B equation, right? And so how this relates to AX equals B is we actually look at the matrix invertibility theorem. And so the thing that you have to think about here is that this cannot be an invertible matrix, okay? This matrix cannot be invertible, and if a matrix is not invertible, then the columns of the matrix are linearly dependent columns, so meaning the columns are scalar multiples of each other. And if the columns are scalar multiples of each other, that means that the determinant of the matrix must be 0. This is, again, matrix invertibility, invertible matrix theorem, okay? And so really, because of that, we know that this matrix, the determinant of this matrix right here, has to equal 0. And because of that, and how the math kind of plays out, you can find the eigenvalues by using that fact. And so, for example, let's do an example right here with a matrix, maybe let's do a 2 by 2 to start, because determinant of 2 is pretty easy to do. Let's say we have the matrix 1, 2, 3, or let's say A is 1, 2, 3, 4. Okay, it's can you see that? 1, 2, 3, 4. Okay, and so AX has to equal lambda x, and so in order to do this, we have to do A minus the determinant of A minus lambda I equals 0. And so remember, I, the identity matrix, this is a 2 by 2 matrix, so our identity matrix, right, which will also be a 2 by 2 matrix, will just be 1, 0, 0, 1. This is our identity matrix, and so if we use this identity matrix, remember lambda I then, right, we put a scalar in front of this matrix, right? This will just be lambda 0, 0, lambda. And so if we do a minus lambda I, right, this will just be determinant of 1 minus lambda, 2, 3, and 4 minus lambda, and then this determinant must equal to 0. And so now, remember, the determinant of a 2 by 2 is just this AD minus BC, so we have 1 minus lambda times 4 minus lambda minus 2 times 3 equals 0. And so now we'll see that this is just a quadratic equation. And so remember, this is the same as lambda minus 1 times lambda minus 4. If you're confused, remember, just factor a negative, factor a negative. Negative times negative is positive, so this is the same as that. And then minus 6 equals 0. Let's just expand this here. So we have lambda squared minus 4 lambda minus lambda plus 4 minus 6 equals 0. And just check if I did that. Lambda squared minus 4 lambda minus lambda plus 4 minus 6 equals 0. Again, it's important to check your work as you do this. And so now we'll see here that this will be lambda squared minus 5 lambda minus 2 equals 0. And so now, again, I didn't expect we'd have to do this, but again, you have to do this in order to, again, you can use a calculator for this, but you can just do quadratic formula here. So we have lambda equals to negative of negative 5 plus or minus square root of b squared, so negative 5 squared, and then minus 4 times 1 times negative 2 all over 2 times 1. And so what you notice here is that because we have a plus or minus, we're actually dealing with two eigenvalues in this case. So there are two characteristic values for this matrix. And so again, now using the fact that you have these two eigenvalues, you can then find your eigenvectors by plugging them into this, again, this equation, ax equals lambda x. Okay, in order to solve for then your x, you do, again, your a minus lambda I times x equals 0, and you just plug in your respective lambdas here, and then you solve your x. You could do a R or EF, get into row reduced echelon form, and then solve for your x that way. And so this is, again, the general strategy of finding your eigenvalues. And so again, you can do this with 3 by 3s, 4 by 4s, 5 by 5s, n by n dimensionalities. And so this is really how you find eigenvalues. And yeah, sorry, quadratic formula here, you'll probably have to do that quite a bit. But again, other cases you can just factor out. Maybe you were given a calculator. That's also, you can just use the calculator to find the eigenvalues. And so yeah, this is just how you calculate eigenvalues. Pretty straightforward until it doesn't get straightforward, because then you'll have to figure out what these do, how do these help you, and then you'll have to do problems, and then it just becomes hell. So this is really the basics of hell. No, this is really cool stuff, but it can get really difficult. Yeah.